Yeah, welcome to the Adopting Apache Iceberg at Slack. I'm Lawrence. With me today is my colleague Fenil. We're both on the data ingestion team at Slack. Our primary focus is to do streaming ingestion. Well, nowadays it's streaming ingestion. In general, our focus is ingestion of our log and event data, as well as our application and incremental CDC data into the lakehouse. Iceberg was my team's first. Our team was the first to adopt Apache Iceberg, and so we wanted to share our challenges today, as well as like the future and how we want to further adopt Apache Iceberg at Slack. And so to do that, we'll give a brief history about like where we're coming from, our stack and our architecture, how we adopted Iceberg, and some of the challenges we faced. We'll look in depth into a few of our learnings and experiences that we have, as well as try to give some general recommendations. And we're going to save about 10 to 15 minutes at the end for question and answers. I want to just say that new technologies always offer a lot of promises, right? They look really cool, they sound really cool, but baked underneath it is a whole bunch of assumptions that maybe we don't necessarily realize. Or we're starting to work in new paradigms or work with new technologies while still holding on to old habits or old assumptions that will actually get us into trouble. That's what happened to myself and to a whole bunch of other people who are starting to adopt Iceberg. Slack is no difference. We're humans. We make mistakes. That's okay. The point is not to like shy away or feel embarrassed or kind of hide it, but to celebrate it, share it. If we did it, you're probably going to also, or hopefully if we did it before you, then you're going to skip that whole hurdle and can just move on with what you're trying to do. So first, let's look at the history at Slack. We've had explosive growth since its inception. I'm actually not legally allowed to tell you the numbers and like the volume of metrics, but what I can say is that if you've watched the Airbnb or the Pinterest presentations, we're in the same ballpark of metrics here. At a high level, we usually use Parquet and Hive. We have Spark processing on EMR for our batch ingestion as well as for most of our compute. We orchestrate a lot of stuff with Airflow. We usually use Trino for a lot of our ad hoc analytical queries and also to power a lot of dashboards. And then we use various tools to get insights and for users to like look and see what the data is happening. A key point here that I'll just kind of mention is that we use S3 data lifecycle policies for our data management. We typically perform these with Terraform to execute the policies and to get them out into production. Our data lake is primarily, although not exclusively, in a single S3 bucket. Each table has its own little prefix. Data's like partitioned, at least for the tables that are partitioned, down to the day hour, sometimes down to the granularity of an hour. Our S3 bucket is versioned. This is because sometimes we'll accidentally delete a file that we want to then undelete. Versioning helps with that. And then data is automatically deleted with the S3 lifecycle policy. First, it's made unavailable, and then after a certain amount of time, it's then fully deleted. So you have like hard and soft deletes, if you've heard that before. Our log event ingestion was mostly a batch process. We did have Kafka in there to like stream. That was our messaging bus. We used Kafka Connect with an S3 sync to write data just raw out into S3. Where we then had a multi-stage process to then like extract, deduplicate, and transform things, make available in Parquet and Hive, and then our downstream stakeholders can use it with whatever tools that they were hoping for. Our application or a transactional database ingestion is actually very similar. So the backend for Slack is Vitesse. That is a sharded distributed MySQL database. And every night, each shard is then backed up into S3, and we use Apache Scoop to then take snapshots of all of these shards every day and make it available into to our lakehouse. We then take those daily snapshots and use what we call a snapshot into the partition table, so you can have longitudinal analysis over the data, and then again made available for our stakeholders for whatever tool that they choose. This has kind of given us a few categories of data. So one is static. Very seldom changes. Maybe it's kind of side-loaded in there. Think like geospatial, like things don't really change that often at least for our use cases. We have the append only. So this is kind of like write once, then read a few times. Kind of you do a longitudinal analysis. This is your DS or date partitioned type of data. Really things that are only like appending to this. And then finally we have like the recreated data. This might be like data sets that are kind of used for quick dashboarding, like in Tableau or using Trino. You want like really fast analysis. You aggregated these prematurely with the idea that like, oh, we're going to be querying these data quite often. So these are replaced several times and were read several times. And so from there, we thought, this is a really great opportunity to adopt Iceberg at Slack. We've encountered a lot of issues that I'm sure a lot of other data engineering departments have over time. The one about like just schema and then especially like partition evolution, like how many times have all of us who've been working with these long tables and have been alive for a long time, being like, oh, well, our read patterns have changed. We need to repartition the table. So let's just migrate the whole table and do a whole write? Oh no, that's a lot. Or maybe now you're supporting 2 versions of the table. I have one that's 5 versions, and it's just terrible. You know, moving to Apache Iceberg, you can solve this in less than half a second, and it's a brilliant thing. There's no like week-long distribution of trying to renegotiate these things with stakeholders. It's just let's do it. Along with it is ACID transactions. That's been super helpful. I mean, think of all like the tech debt and the cruft that we have all developed throughout our entire careers just to try to get item potency and like something that's kind of akin to ACID transactions, and now we just kind of get it for free. That was cool. Data sharing was awesome, trying to get out of Hive and more into an ecosystem that we could share amongst different catalogs. Breaking down our data silos, super important. The performant queries have been big. There have been instances where we've had like 60% reduction just by switching over to Iceberg because of the file pruning mechanism that it has, and then we can do even further optimizations from that, like amazing. And then we have an in-house built write audit publish system that also allows for rollbacks that Iceberg just like supports. So, you know, wonderful. So that's what kind of led us to like using Iceberg, and that's why my team first started to use this one. So I'm going to switch it over to Fenil. He's going to tell you about the current state data in Slack.
Thanks, Lawrence. So yeah, we looked at a few of the projects of how they were at Slack in the past, and now I'll talk more about the new projects that we have built around Iceberg. So while building these projects, one thing we wanted was to not be restricted to just batch ingestion format and just Hive tables, like predominantly used Hive tables for all of its workloads. So we wanted to evolve into a more diverse ecosystems where we can support both batch and streaming workloads, and also wanted to move towards a data storage layer where we support Iceberg tables, Hive tables, and in future even more tables. For streaming, we went with Kafka Connect as our ingestion system. At the first layer, we went with Kafka because Slack already used Kafka for multiple use cases. Our requirements were simple: record in, record out. We were just doing single message transforms. We didn't require any aggregations or complex joins, so Kafka fit the bill perfectly for us. We still use Spark and EMR for all of the batch compute, and all of it is orchestrated on Airflow. And for Hive tables are mainly used for all the downstream batch ingestion jobs, and Iceberg is mainly used within our team in the first data ingestion layer for both batch jobs and streaming jobs. So by moving to this new data format, it gave us a number of benefits. As Lawrence mentioned, for some of the biggest tables, our query performance improved by up to 60%. Our data was landing much faster. In one of the projects, we were just like dealing with incremental set of data instead of like the entire history of the data since the beginning of time. What this enabled us was now we are just working on that incremental change set. And so we are working with very small set of data. This enabled us to land our data much faster. Processing took like upwards of 24 hours for some of our pipelines. Now it's within minutes. Having these data land faster also allowed us to build new use cases on top of it, allowed faster decision making and run faster analytics for downstream. And also cost savings was a big factor. Earlier we ran our EC2 instances for 24 plus hours. Now it's just minutes. So we saved a ton there as well. Another big benefit of moving to Iceberg was the zero copy, where we wanted to allow different systems and different services like Snowflake to use this data, but we did not want to like move these underlying data files to a different system. So using Iceberg catalog helped us in the zero copy where Snowflake can easily access this data without actually moving the underlying data files by just operating at the catalog layer. So this was our first project, which was like log-based ingestion system, which Lawrence explained, where the data was produced to Kafka topic and using an S3 sync ingested into S3. Now, a new project, we call it Icecone, basically Iceberg plus Kafka Connect. And the way it works is still from the producer side, it's the same. Kafka producers what we call as Muron agents, what they do is from different servers, they read these logs and push it to a Kafka topic. Once the data is available in the Kafka topic, we use the open source Kafka Connect Iceberg sync that Tabular provided earlier, and now it's merged with the Apache Iceberg project. And now what the sync does is takes the records from the Kafka topic and appends it to the Iceberg table. We store all of these data in S3, and we use Hive catalog for managing these tables. We run regular maintenance operations on this table. All of them are orchestrated via Airflow, and we use Apache Spark on EMR for running these maintenance jobs like snapshot expiry, compaction, orphan file deletion, etc. These Iceberg tables are like append-only tables, as is the nature of log format. So every row just tells some log from the server where it came from. And then once this data is available, we run all our downstream analysis from these Iceberg append-only tables. Another project was this, where we wanted to consume the data from transactional database. We used Vitess, which is a wrapper over MySQL, and worked on the backups. And this was what I was mentioning earlier, where these backups contain the data from the beginning of time at Slack, and every day we were creating these backups. We were spinning up new MySQL clusters on these backups and then running Apache scoop process to get the data from MySQL to Parquet format and then dumping it into S3. This entire process was super costly for us and also took a lot of time. So now we moved to this change data capture paradigm, and we call the project as Percolator, where now at the source in Vitess, whenever there are these changes that are happening on the table, a row gets updated, deleted, or like created, these change log in the MySQL servers get streamed via Debezium, which is a Kafka Connect source, which takes this change log and then dumps it into a Kafka topic. Once the data is available in the Kafka topic, it's the same as Icecone, where we take the Kafka Connect Iceberg sync and take the records from the Kafka topic and dump it into S3. These tables are again append-only Iceberg tables. We call it CDC table, where now each row is the operation that happened on the Vitess side. So it can be like a create operation, update, delete, and the state of the row before that operation happened and after that operation happened. The catalog is the same, Hive catalog, and we run the same maintenance operations on these tables. But the story doesn't end here. Our downstream, they never had these changelog tables, and they don't really care about these changelog tables. What they really care about is the actual table that's in Vitess. They don't care about the changelog. So once this data lands in the changelog table, what we do is run these merge jobs that take the data from the changelog table and run a merge into query into what we call as mirror Iceberg tables. And these tables try to be exact one-to-one with the Vitess tables. And once the data is present in the mirror Iceberg tables, we have a lot of consumers of these tables. We also don't want everyone to migrate their pipelines. Initially, they were using the Hive partition table to now use the Iceberg tables. So what we do is the same add partition job that you saw earlier, we run that, and we take this Iceberg table and append it into a Hive DS partition table. So this is where we transform the Iceberg table to an Hive table, and then our downstream basically mainly reads from this append-only DS partition Hive tables, runs downstream pipelines and different analytics on these tables without having to do any migration. So the source of the same, the table path, partitioning, naming, everything is the same for downstream. For them, all they care about is these append-only DS partition tables, but now the source is swapped from a batch-based ingestion system to a streaming-based ingestion system. So with these new projects, the kind of tables that are in the data lake are also changing a lot. Earlier, we have like static tables or some tables that we recreated every day, or just these append-only date partitioned Hive tables. But now we have these append-only Iceberg tables, which are downstream of Kafka Connect. The size of this table only grows. We do write them twice because first, at the right time, when we are ingesting these records from Kafka, what we really care about is just matching the throughput of Kafka and just keeping up with it. And at the same time, we also want to ensure that our reads on these tables are fast. So during the write time, first, while Kafka is writing, we immediately write without really caring about the sort order or file sizes or anything. And then at maintenance time, we rewrite these data files so that our downstream reads are not affected. These are used as foundational source of truth for many of our downstream pipelines, or our log tables and change log tables are these append-only Iceberg tables. And then this new category is like of the mirror tables that I talked about earlier, where there is no fixed method of how it's updated. There are random updates, random deletes. Again, these tables are also likely to grow with every new change log that gets merged into the mirror table. We write some of the data files, other files are not affected, and these tables are also read several times. So the initial version of this mirror table, when we want to onboard a new pipeline to Percolator, we use these snapshot-based tables from our batch-based process from Apache Scoop. And we use those snapshot tables to create these initial versions of the mirror table into Iceberg format, and then merge the change log into these tables. And once these tables are available for downstream analysis, as mentioned earlier, we take this mirror table and send it to append-only DS partitioned Hive tables. So this is how we are moving to a more diverse ecosystem where our workloads depend both on Hive tables as well as Iceberg tables. So now I'll go ahead and share some of the learnings that we had while working on this project. First one was, okay, during testing, everything was working fine, but in production workloads, these merge jobs are essentially doing big joins that take the changelog table and merge it into the mirror table. It was taking a lot of time, and we wanted to scale it for our longest and biggest tables. So the one thing we did was use the incremental merge pattern. One amazing quality of this append-only Iceberg table is that we can use this incremental merge pattern on this Iceberg table, where we just provide the two snapshots of the Iceberg table, and we'll just get the rows that were added between those two snapshots. So we use this a lot to just look at the data that the mirror table had never seen. The way we did this was using the snapshot summary object to hold critical information for this. So what we did was a mirror table snapshot would hold the snapshot ID of the changelog table that it has last seen. So when we run the merge query again, what we essentially do is just look at the new records that were added to the changelog table that the mirror table did not see. And we only look at these data frame and then run the merge into query. And this pattern allowed us to scale to some of our biggest tables. Another one was using the storage partition join. As mentioned, merge does this big expensive shuffle between our records. And this shuffle happens on the primary key of the table when you are doing the merge into query based on the CDC paradigm. So in order to avoid this expensive shuffle, what you can do is repartition both the changelog table and mirror table into a common partitioning scheme based on the primary keys of these data sets. And when you do that, the data is already pre-partitioned in the format that you require. Spark doesn't have to actually do this shuffle. So using storage partition join, we repartitioned our tables, both the changelog and mirror, using the bucket transform with some number of buckets over the primary keys. And for some of our biggest tables with over 1 trillion rows, this allowed the merge pattern to work really well. One other optimization we did was enabling merge on read for some of the tables. Our default was copy on write, which worked well for most of the cases. But for some tables, the pattern of updates was such that not many rows are created, but just there are huge number of updates happening on the table. And some days you'd see just that more than 50% of the objects need updating, even though the updates were really small, but you are essentially rewriting the entire data file when you are doing copy on write. Moving to merge on read enabled us to decouple our read optimization with write optimization. So now we are just relying on creating the delete files and not recreating the entire data files. And then we run maintenance at some cadence so that our downstream reads are not affected. Another thing that we observed was there were a number of cases where you would want to delete the data from table. One of the reasons can be some customer of yours want to delete all the data from Slack. When this happens, earlier what we used to do was just relied on the transactional database to run those deletes, and those deletes would be missing from the backups, and we won't just worry about it. But now in this new world, what happens is that delete that happens on the witness table gets streamed to you as a new changelog entry in your changelog table. So you just see that, okay, this delete operation was performed, and this was the state of the row before the delete was done. Now, in order to delete those data from all the copies of the table in data lake, we can't just expire old snapshots of the changelog table, because in append-only workloads, latest snapshot still points to all of the rows of the changelog table. You can't simply run a delete statement to delete all the deleted records from the changelog table, because someone can still time travel to the previous version of the table and retrieve the deleted record. There are other cases where you would want to delete the data if there is you just need 90-day worth of data, or you want to redact some PII information. Even running these statements won't actually delete this data from the underlying S3 file. Someone can still time travel, and because of time travel feature, even Iceberg stores all of this data in S3. So you are not getting any cost benefits or not solving any of the security concerns. The way we solve this for us is by doing both these operations simultaneously, where we run regular deletes to drop the historical data and also run a separate snapshot expiry process during the maintenance phase. Running deletes will remove the record from being linked to any of the newer snapshots in these append-only tables. So when we delete these objects, then the data is still present in the past snapshots, but all the newer snapshot will not have that data. And when we do the snapshot expiry, it will clean up all these old snapshots that link to the deleted records. And while cleaning up snapshots, if Iceberg realizes that this data file is not linked to any of these snapshots, any of the active snapshots, then it would go ahead and remove the record from the table entirely, along with all the underlying data files. One other problem that we saw was Kafka lag. In some cases, was just hanging to a constant value. It would not go down. This was observed while consuming from the Kafka topic in our Kafka Connect Iceberg sync. This was happening for tables, for topics with extremely low volume of records, think 2 to 3 records per day. We would always observe a non-zero lag where the open source connector would never actually consume from the Kafka topic. Now, in order to talk about the solution, I'll first explain how the Kafka Connect Iceberg sync works. So it essentially reads data from Kafka partition and commits to the Iceberg table. But the way it does it, there are worker tasks which read data from Kafka partition, and they just write files to the distributed storage. In our case, it's S3. And there is a coordinator task which is responsible for gathering files and actually creating the Iceberg commit. So in order to facilitate communication between the two, they have this internal control topic where the worker and coordinator each send messages to each other. So there are two different set of consumers here. One is Kafka consumer for the control topic. All of it is internally managed by the open source code. And the other is Kafka Connect consumers for the actual data topic where the actual record resides, which is handled by Kafka Connect. So the solution was, what we were observing when this happened was Kafka would continuously rebalance all the consumers. And this happens if the consumers don't send regular heartbeats within a configured session timeout interval. Heartbeats are sent as part of separate thread when we call poll process on the consumer, and the open source Iceberg connector only call these polls when either there were record in the data topic or when there were regular flushes happening. These flush in Kafka Connect had a default interval of 60 seconds, but the session timeout for Kafka was 45 seconds. So what you would see is after every 45 seconds, Kafka broker would realize, okay, that consumer is not active, and it would trigger a rebalance. And we ended up in this constant cycle of getting rebalanced and never actually consuming from the topic. So the fix here was simple. We just had to increase our session timeouts to be greater than a minute, and we set it to 4 minutes. And then this hanging lag problem actually went away for us. Now I'll hand it back to Lawrence to talk about some of the other challenges we faced.
Thank you, Fenil. Yeah, so a couple other challenges, or maybe some oopsies that we made. Sometimes we made the data set unreadable. If you remember back to our S3 lifecycle policies, we were trying to manage volume proactively by deleting data as a soft delete and then deleting it as a hard delete. Iceberg changes the game though, right? Like your metadata used to live in the Hive catalog itself. Those two things were coupled. Now the metadata lives in S3 co-located with your data files. And so the S3 lifecycle policies will find your manifest or your metadata files and try to proactively delete them. This can be a total or a partial outage depending on what it deletes. If it deletes a manifest file, actually you could probably be fine. It's a partial error until the actual query planner tries to open up the manifest file and finds out it's not there. You're totally fine. But other than that, you're only getting a stack trace. If it deletes the metadata file, that's how it tracks what schema the table actually has. You may not be able to do that. Iceberg doesn't yet, as version 2, have like a recovery process. So the only thing you can do is, if you're using a version bucket like us, try to revert or undelete the object before it's permanently deleted. If it's gone, sorry. I think you can maybe do a partial recovery or try to do like some Parquet fanciness to try to make a new table, but things aren't looking too good. So yeah, be sure to update your S3 lifecycle policy to not delete the version. Let Iceberg try to actually like put the delete markers on the S3 files. That was a good learning. We've had issues where we didn't optimize for the reads. So yeah, we're using Kafka Connect, right? We're writing lots of tiny files. So we kind of need compaction, right? Reads, we know from history, are generally better at 128 to 512 megabyte Parquet files, maybe a gig, kind of preferences there. But we're typically writing on like the order of like, a few kilobytes to maybe like 50 megabytes at any given file. So we definitely want to compact that. So we started running compactions about every 3 hours, just so that we were always trying to keep up with cleaning up these files. And yet we were still finding really small ones when we went to go and like personally investigate. The problem with more data files is that it means more manifest files. And more manifest files means that your query planning times are going to take longer. So if you're running compaction on a streaming process like what we're doing, you really want to try to make as few files as possible when you're compacting. And so what we found is that the Iceberg maintenance actually has some defaults under the hood that we didn't realize, right? We just kind of heard, do compaction, rewrite the files, you're fine. But there's a minimum on both the size and the number of input files before it actually does a compaction on a partition. So be sure to update your settings and when you're calling the rewrite data set files. We've had issues where maintenance is taking too long. We've had a couple instances. Excuse me, the first one is a mistake that we made. So Kafka Connect is just a config. You write a config, it starts moving data, awesome. What happens when that config is improperly configured, right? It's JSON, English, we look at it, we say like, oh, this column exists, and then Kafka Connect says this column does not exist, but I'll still create your table, and then just won't do any partitioning, even though we specified it. Like none of the partitions worked, even though I misspelled only one column. So that was too bad, and none of us caught this. What happened is that the data eventually filled up over time. It had about 50 terabytes, and then we started getting failures on our maintenance job, saying that it was taking too long, there were retries, and then we look and it's like, oh, yeah, files are being compacted, what's going on? So luckily, we were using Iceberg, right? You can adjust the partition strategy kind of on the fly. Alter table, add partition field, done. And this time I spelled the column correctly. The next time the rewrite data file happened, it was able to repartition all the data files correctly, and then ongoing maintenance, totally normal, as we expected, right? So the learning here was definitely to monitor your schemas and alert on any discrepancies. I think this is just a good general practice, even if you're not using Kafka Connect. But yeah, that was a good learning. The other one was that you should turn maintenance on, which might kind of sound like a duh moment, but you have to understand, like, we didn't design this whole new architecture just like one day and be like, great, we're doing this, we're off, right? It was a very slow, iterative design process. We had like a concept, then a POC, and then a dev, and then a production. So there's kind of cruft in each of these steps that gets kind of left over the ages. There's one data set that we had in our dev environment. It's a pretty high volume topic, and so it was writing files every 5 minutes for about 6 months, right? So lots and lots and lots of tiny files. And when we came time to actually turn the maintenance on, it just kept crashing. The driver just ran out of memory. And so we were like, well, why is the driver running out of memory? This seems like a pretty simple operation on a dev table. And then come to find out we have 12.5 terabytes of manifest files. That's just metadata. That's not even the data itself, right? This is all just pointers to where all the little files are. So, okay, well, just give one driver a crazy, obscene amount of memory, let it finish the job once, and then after the manifest files are done, the compaction is done, we rewrite the manifest files for the smaller number of data files, everything's beautiful, maintenance is back to normal, right? Just reduce the memory back down. But yeah, start maintenance early and run it routinely. That was a good learning. We've had issues where data is growing more quickly than we had realized. So yeah, we're committing data from our streaming services every 5 minutes. And retries can happen for a streaming service for a variety of reasons. Kafka Connect, we're running it in Kubernetes clusters, so pods are ephemeral. They pop in and out of existence all the time. We have AWS rate limiting issues. I'll talk about that one in a second. That was fun. Sometimes we have parsing errors because we do some transformations on the wire before we actually write to the Iceberg tables. Something can happen there, and then you just kind of have this file that was partially written to, but because we're using Iceberg, it's not linked in a manifest file, so it's there and you're paying for it, but can't use it, right? It's too bad. So what we discovered was that like orphan files are actually quite prevalent, probably more than you're expecting. Failures don't happen just in streaming services too. This will happen in batch. No matter what you're using, if you're writing to an Iceberg table, chances are you're going to have orphan files. So that was our big takeaway, is like definitely run maintenance for orphan files pretty routinely. You don't have to do it every like 3 hours. We do it on a weekly basis. I would suggest at least monthly. The other one though is that we also found out that non-compacted files take up space. I mean, there's data there, so of course they would, but after you run compaction, what happens? Iceberg, every action that you have that happens to an Iceberg table issues a new snapshot, right? It's a new commit. So you can time travel to a previous snapshot, even though it's the same data. So the current snapshot has the bigger files, the previous snapshot has all the really tiny files. Well, we don't need that anymore, right? So we're now having doubled the amount of space that we're taking up that we don't need for the like equivalent data. So be sure to kind of clean up your old snapshots as well, especially for append-only ingestion. And then my personal favorite, because I did it, I took down all of our analytical data processing for about 3 hours because Iceberg lets you wield a lot of power. Small history here. We have one data set that's quite voluminous. It does telemetry tracing, so we just call it traces. It was initially just a batch ingestion or a batch ingested data set. And we had some forethought in designing it. We partitioned it based on a column to help downstream reads, right? At the time, cardinality was pretty low, but over time, that cardinality really grew. We're talking like 10,000 plus, right? So every day we're writing about 10,000 different partitions, and there's heavy data skew. Total, I forget what it's called, the 90-10 or the 80-20 thing, right? Like 20% of our partitions carry 80% of the data, and there's a horribly long tail. When we switched over to streaming service, we also wanted to try to tackle this data skew a little bit, right? Because they're just inefficient for the writes. It's not very good for the reads either. So, all right, now we're writing every 5 minutes from all of our tasks. And we're like, well, Iceberg has this new like bucketing partition strategy. Let's try that. And so we chose 200 just because, 200 out of 10,000, that sounds like a pretty good trade-off. And we can always change it, right? We can adapt to this on the fly. So the skew still exists, but to a far lesser extent. Now everything's just kind of bucketed into 200 fields. So day one, we launched this into production. Things are looking good, but we're noticing that the Kafka Connect is experiencing some lag. I think if I'm remembering right, we had 200 partitions. We started with 50 tasks, and so we have the ability to scale up to 200, but we're just like, you know what, let's just double it to 100. Every task deals with 2 partitions, and every task is now writing every 5 minutes. The second day, we're kind of working with the stakeholder, and they're like, hey, we're noticing some great performance so far with this bucketing of 200. What happens if we do it to 400? Well, what normally would have taken like a week to try to like renegotiate and like try to like make a table and then do like a comparison like an A/B test, we're just like, well, let's just update the scheme and just collect some data for a few hours and then see what happens. So I issued this command, the alter table command, and left for lunch for an hour. And when I came back, everything was on fire. What happened was that we were getting AWS rate limits like crazy, not only on the Kafka Connect portion, but across like all of our analytical processing, right? Our Spark jobs, both read and write operations, were experiencing this like high failure rate, everything's getting retried, and it only adds to like these queues, which then hammer AWS more, right? So it was kind of like a downward cyclical spiral. When we finally fixed the issue, here's what we found. With the batch job, right, we're writing at least one file to 10,000 partitions once an hour. So, okay, 10,000 files per hour. When we launched with Kafka Connect, we had 50 tasks for over 200 partitions, and we're writing this every 5 minutes, right? Let's just say worst case scenario, every partition has a piece of data for, each task has a piece meant for every partition in like every bucket, right? So you're gonna be writing at least to every partition per task. So now all of a sudden every 5 minutes we have increased from 10,000 to 120,000 files. And then when I doubled both, now I had a 60x increase, and AWS did not like that. Now S3, to give their credit, I know we have AWS people here, S3 is awesome, right? It can take so much data, so much volume, and like we just kind of all take it for granted because it works so well. But you have to remember, there are literal computers behind the hood that have to deal with this, and so that's why there's rate limiting issues. They have like this concept of a shard. It's a black box, but what happens is if you send too much data to the same shard, they say, no, you have to slow down, and there seems to be like this Levenstein or lexicographical boundary that's how it affected. So if you're within the same bucket and you're starting to hit one area too hard, that's why it's going to affect all of your other processing or all of your other data sets, because they're all going to the same boxes under the hood. So our recommendations here, try to reduce the number of Kafka Connect's tasks. That'll help reduce the number of files that you're writing. Try to reduce the number of partition buckets that you have. Iceberg does have a kind of a hidden storage option if you look into the settings called object storage. And what it does, it kind of salts the path for S3 so that it's more likely you're going to evenly distribute data across different shards in S3. Personally, we didn't have good luck with that, but I have seen instances where others have. So, give it a shot. You can always turn it off. Like I said, Iceberg's very adaptable. And then one thing that I would really encourage is try ordering over adding more partitions. When you're doing streaming ingestion, the ordering and what it does is it groups similar features within your column together. So not only do you get better compression, but then you also get better file pruning. So partitioning plus ordering better file pruning on both ends, that's what you really want to get the read performance that you want. We're just kind of used to partitioning as a knee-jerk reaction because of Hive. That's the old world, all right? We got far more options now. So yeah, try that. It'll probably increase the likelihood of file pruning, and it'll get better compression. So, okay, do a time check here. My watch is telling me to relax. I must be stressed. Okay, so our general recommendations across all of this. I will say, if you have a stack similar to ours, or if you're doing things that are similar to us, these might be a benefit to you, right? If you're knee-deep into it now, or if you're about to start your journey, try some of these recommendations. I think you'll get really far really fast. But you have to understand, Iceberg is generally applicable, but adopting it is not. It's very stack dependent. It's very use case dependent. What we're doing today might not apply to you, and that's totally fine, but take it with a grain of salt. I'm listening to everybody else here at these conferences today and tomorrow, taking what you've done with a grain of salt too, because I think there are things that are overlapping here that I definitely want to adopt. So first and foremost, update your legacy lifecycle policies. Don't accidentally delete your metadata. Let Iceberg manage the data and the deletes. If you are using a version bucket like this, do the hard deletes after Iceberg does the soft deletes. Run maintenance early and often. You definitely want to try to remove previous snapshots, try to keep past data in order. Remove orphan files, they are more prevalent than you think. Rewrite manifest files from time to time. It's a good order just to kind of keep that condensed. And then, yeah, definitely for compaction, do give appropriate resources and allow for partial progress when you're doing it. Try to specify time boundaries so that you're not doing the entire data set, but just the portion that you've recently in there. And now, kind of new to us, you have to be mindful of your data and access patterns. Use merge on read to try to increase data freshness and to try to decouple the read performance from the heavy and repetitive write operations as you're updating data. And definitely think carefully about partition and data skew. Consider ordering to also increase the file pruning. So I'm sorry we're rambling quite a bit. We love to talk about this stuff. I know we have a few minutes left for Q&A, but thank you all for having us.
Thank you, Lawrence. That was great. That was an amazing talk. All right. We have 5 more minutes. We can take a couple of questions.
Hey, My name is Dennis. Yeah, thank you so much for the talk. A lot of very useful insights. I have a good question regarding, you mentioned CDC, and you mentioned that you have like complex merge jobs that's expensive that you're running. Now I'm curious why you have not or have you considered moving CDC to Kafka Connect, and what stopped you, or have you tried it?
Yeah, we did try it, but as we mentioned earlier, so when we are reading from Kafka Connect, what we essentially want to do is like have these updates and consume it as fast as possible. So appending to a table was much easier than either like deleting or either like updating or deleting these records from the Iceberg table. And then once we have all these batch records, when we actually run the merge jobs, we are actually decreasing our write amplification a lot, because now we are updating bunch of records at the same time on the mirror table.
But you also mentioned merge and read, that you're using that. Have you tried merge and read with Kafka Connect?
Yeah, but again, for that, even with the delete operations, we did see for some of our largest workloads that it wasn't scaling well. And again, these changelog tables are also used downstream for some of the different use cases. So it was good to have both of these changelog tables and mirror tables. I know there is a blog which explains, I think it's from Ryan, about how this CDC paradigm with Iceberg first putting tables into changelog table and then incrementally merging them into the mirror tables scales better than directly doing it at the sync level.
Gotcha. Thanks.
All right, one more question.
You mentioned in the beginning that you had just one S3 bucket with different prefixes. Was there a reason not to go with multiple S3 buckets so as to not hit the rate limits?
Oh, that's a good question, and actually this goes well before my time. I will say we do use more than one bucket. It's just our data warehouse is primarily in one bucket. I could look in the Slack logs to see this conversation as to like why that choice was made, but I don't know if I can give it today. Follow up with me later. I'll try to find it. We can talk online. The AWS rate limiting, yeah, splitting it up by bucket or to separate buckets would help. I know we've also talked with the AWS people about using the new S3 tables, which just have a much higher rate limit to it. Their product offering was not a good use fit for us, but it may be for you if you are looking at like very high rate limits. That's something to look at. But yeah, I think just different naming schemes, salting the path. That tracing example that I gave, we did hit a rate limit. But actually very easily we're able to like bring it back down, and our data volumes are still growing. We're still deploying new pipelines to this. Like we are definitely increasing substantially how much we're writing to S3 and haven't hit the problem again. So I think between the tweaks, the tweaks and configurations for Kafka Connect and also for Iceberg can very quickly cause an S3 rate limit. It can also stop one very quickly too, and you can adjust very quickly.
Hi, I'm Rahil. I have a question about your mirror tables. What are, in general, the SLAs that you see for a commit that happens in MySQL for it to flow in the mirror table?
Yeah, so first at the Kafka Connect sync level, where we first ingest this data into the changelog table, we have a commit frequency of 10 minutes, and then we run these hourly batch pipelines. So they take all the data from the changelog table and update the mirror table. So typically it happens within 1.5 hours, but we have our SLAs that all these merge jobs every hour are successful within like the 3-hour mark when they are run.
Okay, thanks. I have a follow-up. Do you have any mechanisms in place to ensure that every commit happening in MySQL lands in the Iceberg table? How do you ensure like?
Yeah, that's a really good question. We do that by, the initial batch ingestion system that we said, it's still around, that for many of our tables, which land these data, but it's just much later than the streaming-based system. And once both these data land for the given date, what we do is we compare the entire data row by row for all the columns and ensure that it's still one-to-one to see if we have not missed any of the record in the in this entire new pipeline, streaming-based pipeline.
Thank you.
Hello. Thanks for the presentation, by the way. That's great. Question on the CDC replication portion of your presentation, specifically from MySQL to Kafka Connect. Did you guys experience any issues if and when like MySQL, like a replica, will do a failover? And if you guys did experience that, how did Kafka Connect, or how did you guys recover from that?
Yeah, so at the source level, that's like a different team that takes care of DBZM connector that we use that read from the MySQL shards and pushes it to Kafka. So I'm not an expert on like different cases that we have ran into, but we have ran that like multiple times where something happens that breaks in DBZM. Either like in Vitess, a shard gets split, the upstream team runs a shard split, and some of the records during that shard split are missed. But like DBZM ensures that like in Vitess there is this VGT ID which orders all the rows, which orders all the transactions that are happening on the changelog table within that same shard. So it ensures always that VGT ID sequencing is always continuous. And if that fails, then it just like rewinds the VGT ID, which is kind of like an ordering column, which you also use in our jobs to like order rows, like what happened, like in order to know what event happened later than some other row. And that is like our main mechanism, like at every different step to ensure that we are still continuous.
Thanks.
All right, thank you so much, guys. Lawrence and Fenil, thank you so much for this call.
Thank you.
Yes, thank you all.